Yeah, thank you very much, and thanks to the organizers for allowing me once again to be here. It's really a great pleasure. CATS models, the third one today, talk. So I wonder if, so here he is. I wonder if he understood when he wrote down his model once, how much would follow from that, many interesting questions that could be interesting. And you recognize a middle-aged Boltzmann and perhaps also middle-aged Maxwell. And here, I don't know if you recognize these guys. So this is Nordheim. Let's see if I can get, oops, sorry. So this is Nordheim, Uling, Uhlenbeck. So now you know where I'm aiming at, so which are quantum statistics versions of the Boltzmann equation and the CATS model. And this fourth guy here is Léon Briand, who will also appear at one point in the end of this talk. And
what's the fourth?
Sorry?
What's the fourth?
Briand.
Briand.
Léon, not his father, so I guess this is the famous one. I'm really, you always hear people mentioned by their last name, and some of them are families, so yes. So these are some things I will talk about. This is really classical. It's no quantum in what I'm going to talk about, like Eric. It's just the statistics that resembles quantum. And so here is an image from the paper by Nordheim, where he wrote down really the Boltzmann equation with these quantum statistics modifications, depending on the density here so a plus here corresponds to Bose-Einstein statistics and a minus to the fermionic case. Which is what we have here, and you know that the equilibria to that equation look like this, or like just an indicator function if the energy is low. And so now one can wonder how to derive this equation. So you can do that at least formally from the Schrödinger equation. There are many authors who have done that, and I don't mention them. And I don't know, Eric, if you would get this from your model.
No, with our model that has Boltzmann type statistics in it.
Yeah.
So no.
No. Anyway, for CATS-like models, there are papers, for example, by Pulverenti and his co-authors. And so I should say also excuse to everybody who has heard a big part of this talk before, because there is really not so much new here for some of you, but something at the end which is related to the word inclusion then. Because so here is the CATS model. As Eric mentioned, you have a phase space. So here I should really have had R. No, it's R here. So you have a phase space which is a sphere, n-1 dimensional sphere, to correspond to an energy shell in Eric's. And you have a Markov jump process where you pick a pair at random with exponentially distributed time intervals, and you make a collisions that involve two of these coordinates, rotation of to conserve energy. And so here is what it is, and I'm going to jump this quickly because I'm going to move from the sphere to conserving just momentum as the previous talk there. Now, what would an exclusion principle in this really classical case would be to only allow configurations where the distance between two coordinates, two particles, is bigger than some number. That should depend on the number of particles to get something reasonable in the limit. So this is what we have. We have the distance between Vi and Vj bigger than epsilon, and inclusion. So this exclusion, we will see that will lead in the limit to something that really resemble some Fermi Dirac statistics, but I will also talk about models that would mimic Bose-Einstein statistics. In this case, they should favor clustering of the particles then. Or you can discuss more general models where you had collisions, so maybe it's also in the talk of Emmanuel, you might have selection of particles, the rate of collision pair that would depend on some function that describes the preference of a variable to be at some place or some relation with the other ones. So these are things that perhaps have been discussed by Toscani and many others in these wealth distribution models, for example. So, but it's not really in this talk. So instead, I'm going to move now from the sphere to a model that lives in the simplex. So that's if you just consider the energies and you have conservation of energy by saying that, sorry, I'm not used to this pointer. So you are in simplex here, so you have each xj corresponds to the energy of the particle then. And so you have the model here, you pick a pair as before, and you choose one of them after collision to be anywhere between 0 and the sum of the previous energies, and conserve energy. And you can prove that in this case, this is of course understood that this converges then to the uniform measure on this simplex, and the one particle marginals are beta distributions. Now here you can now include the exclusion principle, and that is really, you have the simply for 3 particles the simplex is just a 2-dimensional figure, and the excluded areas are very clear. Here for alpha equals to 1/2, and so you perform jumps only if the velocities after collision really belongs to this side. So you can make a picture also for 4 particles. Then this is some kind of 3-dimensional object where you can also see sort of, and you can start, same thing. Now, here, of course, if you have a fixed size of the particles, you can't pack them too closely, and so that means that there is a minimal energy, which is epsilon times this quadratic factor here. So, so the energy that you have, so you assume that the total energy is En. It must be bigger than this minimal energy to have any space at all, and so we call this excess energy here, and it's described by this factor alpha n, and I will let alpha n be equal to a constant in the end here. So I have this here. So again, and let's see, time is running. So we have this simplex with excluded diagonals, say, and empirical measures on this. And you might, so you can see that this exclusion says that, suppose you have these empirical measures for that, and this converges to something. Let me step one further. It converges to something. You cannot have the density for this limiting measure bigger than 1 over alpha. This is what you recognize also for the Boltzmann equation, right? For fermions, that you have a limit for the density. And we asked questions about this, Eric and I. So, for example, so you take the limit of this empirical measure for the uniform distributions. Can you compute that? Is there a Boltzmann equation? And we have propagation of chaos. for that, and we answered some of these questions. So here you can see the limiting distributions. So here is for alpha equals 0 with no excluded area, so it's just an exponential e to the minus x. And if you have alpha cannot be bigger than 2, because then things break down. You don't have any. So if alpha equals 2, you get just an indicator function here. But otherwise, you see different scales here. And you can compute this. We cannot compute this explicitly, but there is this function phi, defined exactly as this, and the invariant measure can compute it in terms of this phi with this formula. And there is a theorem saying the following, that suppose we take a family of probability measures on this simplex with exclusion, then this measure, this family is alpha f chaotic in detail. And I would say what that is, where f alpha, it depends on alpha, is exactly this function that you saw in the picture before. And we computed also the rate of convergence here in the Wasserstein distance. So I should say what chaoticity in detail is then, because it's a little bit important. So you have, Manuel told us about the Schnittmann's result here on that chaotic sequences in Boltzmann's or Katz's definitions is equivalent to convergence of empirical measures in law. And so here are two definitions then. So here we need a notion that is sort of coherent with the underlying structure. We have all the measures for a fixed number of particles, n should be on this simplex with excluded diagonals. So that's encoded in here. We alpha f chaotic, so we have this alpha that says how big the excluded diagonals are. So the definition is that the empirical measures converge, in this case, in probability to some density f. Now, in detail, it says how does this convergence happen in some more. So that is, if you look, so if you pick a point x, you think of a finite number of variables now, you pick a point x, and you look at how big is the gap, how much space is it around this point before the neighbor, and you divide that by the expected size of the gap. Then this should converge to a Maxwellian, an exponential distribution in the limit. This happens always when you have a real empirical measures where you take independent, you take n independent samples, right? The distance will be exponentially distributed, but it's not necessary for the Schnittmann definition of convergence of empirical measures. In our case, to get the Boltzmann equation, we need that. So that's just another definition. So let me speed on. So how do you, in practice, sample from this SEN epsilon? So there is a formula for this. This is the factor here saying how much of the excess energy, how much energy you have above the minimum energy, and you have the ZJs here belonging to standard simplex, and you have this formula, and you can prove then that you have good properties of. I mean, this is known for distribution of the simplex, and these help you to prove that this is that the first of all, that really this gives us a sample of a point on the SEN, and also it helps you to prove the theorem that I stated before. So now, so that was the equilibrium measure. So then you can ask, if you have other functions, can you construct alpha G chaotic functions for that? And just first of all, to have anything, we said before that it has to be bounded by 1 over alpha for these functions to be satisfied. So now, so we take any function G that's at any probability density bounded by 1 over alpha, and compute its cumulative distribution function. And if you look at this expression now here, so here is how much of the mass that you have above the point X. And this is really how much space you have between the particles at the point X. So what this function says that if you open up a bit of a space between two particles, you have to move all the other particles up as well. So this says that if the space that you have between particles close to the point X, how much does that contribute to the excess energy? So so here, so h of x is then the distribution of excess energy in this model. And you can see in this picture here, so here is the equilibrium distribution, and here is the excess energy. And you see that for the equilibrium distribution, this is constant, the ratio in between. So that really says that the equilibrium distribution means a uniform distribution of the excess energy of the available space, if you like, here. Yes. And now you can compute the and this is, you check that this is also a probability measure, and it has a cumulative distribution function, and we define these functions here, which are computed in terms of the capital G's and small g's and h's, and then you can prove that if you take n independent samples from this distribution, psi was this function, and you take the difference between these, and you use the same formula as before that you saw for computing the x's from the z's, then you get a sequence, and you take the corresponding empirical measure, then this will be alpha G chaotic. So you have these, and now here is the equation again. You had the phase space for n particles, you had all these, and the jump process, and exclusion was to perform jumps only if the position afterwards would belong to this space. And you get the Boltzmann equation then. Formally, you write it down, and it looks like this, like the usual Boltzmann equation. Here is the collision operator, then you have the gain term here with a factor in front, and I'll take the next. Here you have, yes, you have the values of x and y after collision, and you have this function pi here. In pi you have put alpha times g, and it looks like this exclusion factor. Of course, in the Uling-Uhlenbeck equation, this is the exclusion factor you have then, exactly. So this says that here there is a sort of picture of this that explains what happens here. So if you try to park a car along a road and you don't have indicated places, people just put the cars just anywhere, then you lose a lot of space because you will have a lot of gaps between the cars. That's almost enough for a car, but not quite. Whereas if you have indicated places exactly and people follow them, then each car takes as much space as it has to, no more. And so this factor corresponds to the lack of space. So there are many gaps between particles which are not big enough to put a new particle. So that comes from this. And, and to compute this exactly, you have to know then the distribution of gaps between particles, which is why you need the notion of detailed chaos to obtain this. But anyway, when you have this, you can check by direct calculation that this invariant measure really solves the Boltzmann equation. And you need this exponential gap distribution. And there is an entropy for this as well that looks somehow a little bit like the entropy for Fermion Boltzmann equation. Right. We still have not really proven that this holds now. Simulations indicate that it really happens extremely fast, that you get these exponential gaps. Now, so here, now there was no quantum, and it's just exclusion, right? And so you don't really need quantum to get the Fermi Boltzmann equations or something like that. The really big difference between classical and quantum case is really these questions of classical particles are distinguishable and bosons or fermions are not. So this is what you learn in statistical physics, right? When you derive the distributions for fermions and bosons. And so like this, just, you all have seen this. So here is just one example. You have 3 particles in 4 possible states. So if you really know you have 1 red, green, and blue particle here, you have 64 different states possible. But if they're not distinguishable, or have many of these states will be duplicated. And in the quantum case, these duplications really don't count. So you have instead only 20 for the Bose-Einstein case, if you remove duplicates. And for the fermions, much fewer, because you only allow 1 particle in each state, right? So you have seen this. And so here is now enter Brillouin. So he says, I don't know if you can read this. In classical physics, particles are distinguishable. And then he says that in the new statistics, this was in the 20s, there is the hypothesis of projectiles, is projectile, which are indistinguishable, he says. And he says that this corresponds to a process that is not realizable, so he doesn't like this idea. And he tries here to find a way of deriving these distributions without this, as he thought, this hypothesis that he didn't really like. And so this is probably more history of science than mathematics or physics. This is quoted from a paper by Costantini and Garibaldi. So it's in studies in history and philosophy of modern physics. So anyway, so what he said then was that particles are distinguishable but different in volume. So classical particles have 0 volume in his model, whereas fermions have positive volume and bosons have negative volume in phase space. So then you can try to, if you try, suppose you have the energy levels and then particles, you have these total number of states, and so then it's combinatorics. You put the first Ni particles into level I, so you do that, you lose or gain. So for fermions, you lose a bit of space every time you put a particle in a state. So you just keep adding the multiply, and you get when you have put all the particles in these spaces, you get this formula. Of course, when A is equal to 0, for classical, you would have to multiply this into the gamma. Yeah, I'll speed up. I'll speed up because what would so Anyway, physical or not, inspired by Briand, you can think what happens if you put this alpha, this exclusion term here, to be negative. What you get is that, so what looked like this before, looks like this now in the two-dimensional case. And that means that the states in the middle here, when particles are very close, then you have overlap between. So each of these 6 triangles here correspond to a map of one of the points Z1 to Zn. And you get all of them by permuting the variables, 6 in this case. And here the permutations, when alpha is negative, will give you overlap. So, and yeah, it's in 4 dimensions then. And so you can then sample from this, do exactly the same calculation for difference here with alpha is -1. You see n equals 3, 4, 5, 6, and then you approach the black curve here, which is the limiting function as we had for the alpha positive case. And so here is what it looked for alpha negative. You have the limiting function f here and many oscillations that close up to here. So yeah, let me speed up then, skip this, and say so now the question is, what would be the Katz model? What would be the dynamics for this? And so the inclusion factor here would be, I would like to perform jumps according to multiplicity. If a particle sits here, where the multiplicity is 1, or rather I should say, here the multiplicity is 6, here it's 4, and here it's 2, it would like to sit longer time where the multiplicity is high. So I would like to have, the jump rate depending then on the multiplicity of the point of phase space where you're sitting. And the multiplicity, you can explain exactly what that means. It's the number of permutations such that this holds, that you have the first particle positive, and then the other ones satisfied, because the n+1th particle cannot be too much to the left of the nth particle. So you have this condition, and right, and so you have different ways of trying to do that. Let me speed then, because I wanted to say. Yeah, so this is sort of looking at the all particles at the same time. But if you want a Katz-like model, you would like to do what happens with 2 particles. At what rate do you pick a pair of particles? At which rate do these collide afterwards? And so let me define here. How sharp, I must know how gentle you are with my time.
1 minute?
1 minute, okay. So, yeah, so let me go here then. So I have defined here, so mx is the multiplicity corresponding to a point x, like that. Xij, so here x denotes really the set of these points. Xij corresponds to this set, and Xij tilde to this set with those 2 particles removed. And you can compute the multiplicity according to the formula for any of these sets, and I define the ratio of these. So, so in the end, I would like to select particles. So this factor then says, what is the difference of the multiplicity if you have this pair of particle in place or not? So how much does the multiplicity increase when you add the particle to a place? And how much does it decrease when you remove them? So this should sort of give the rate at which you pick particles in this model. And yeah, so the jump rates should be to the one of these ratios then. I'm sorry for, but of course, the Boltzmann equation with inclusion, I would like to have jump rates coming from this. The inclusion factor here, this I think works, actually, if you put alpha negative. But I have no way of trying to prove that this model would give that, and yet, anyway. The invariant measure certainly works, because that's all the calculations are just algebraic calculation that does not depend on alpha. The entropy, of course, would be problematic with alpha negative. But the entropy is problematic for bosons anyway, so maybe it doesn't cause a big problem. Yes. And here are simulations. So my computer programming for simulating this checks all permutations. And so it's not very efficient, and I cannot use that for very many particles. So here is 6 particles. No, even not 4 particles, but you get something with this calculation anyway. Yes, I'm sorry for not having time at the end to say something more about selecting these particles, but maybe we can discuss at some point. Thank you very much for listening.
So, time for a quick question. Yes, please.
Yeah, so what about this picture, please?
This one. These are nice birds. So it doesn't have very much to do with this talk, except that sometimes you model also swarms of animals with similar models. So thanks for the question, but these are nice pictures.
Okay, I suggest that we move further questions to the coffee break, otherwise we have to skip coffee.
Yeah, it would be.
Well, thanks again.